Dear students, welcome to the today's class of phenol. In this session, we are going to know about the definition of phenol, classification of phenol with examples, then acidity of phenols, and the effect of substituents on the acidity of phenols. Phenols are the molecules that have a hydroxyl group attached to the carbon atom of an aromatic ring. By definition, a phenol is a hydroxybenzene, and phenol is the common name for this compound hydroxybenzene, and in IUPAC name it is benzenol. When a phenol molecule is substituted with additional groups, either the ortho, meta, para system or the numbering system can be employed, or in either case, if the parent molecule is referred to as a phenol, the nomenclature being used is the common system. Whereas in IUPAC nomenclature, substituents are always numbered with the hydroxyl group at the first position. Coming to the classification of phenols, based on the number of hydroxyl group present, it is classified as monohydric phenol, which contain only one hydroxyl group, and dihydric phenol, like which contain two hydroxyl group as in catechol. Then trihydric alcohols or trihydric phenols. This type of phenol contain three hydroxyl group. Say for example, fluoroglycinol. Continuing with the nomenclature of phenols, how to name these phenols. So first thing is we have to locate the position of the hydroxyl group attached to the benzene ring. The benzene rings attached to more than one hydroxyl group are labeled as di, tri, tetra to denote the number of hydroxyl groups. In case of substituted phenols, we have to start locating the position of the other functional groups with respect to the position where the hydroxyl group is attached. So depending on the position of substituted functional group with respect to the hydroxyl group, words like ortho, meta and para are used. Let us know about the acidity of phenols. Unlike the alcohols, which also contain an hydroxyl group, phenol is a strong acid. Phenols turn blue litmus into red and react with metals, liberating hydrogen. And phenols behave as acids because of the presence of more polar OH group in them. And phenols also can ionize in aqueous solution and gives H plus ions. See this sp2 hybridized carbon atom of benzene ring attached directly to the hydroxyl group act as a electron withdrawing group, and electron density decreases on the oxygen atom of OH group, which results in increase in the ionization of phenols. The phenoxide ion formed is stabilized by the delocalization of negative charge due to the resonance in the benzene ring. The phenoxide ion has a greater stability than the phenols due to the resonance. The greater acidity of phenols can be attributed to the resonance stabilization of the phenoxide ion, which is formed after losing the hydrogen ion. The negative charge on the oxygen atom is delocalized around the ring. The benzene ring helps to stabilize a negative charge on the phenoxide ion, and this makes phenol more acidic. Now let us learn about the effect of electron withdrawing group on the acidity of phenol. Substituents actually have a great effect on the acidity and basicity of the compounds. They can either increase or decrease the acidity of phenols. Substituents are of two types as electron withdrawing and electron donating. The electron withdrawing groups are the one which pull the electrons from the ring and decreases the electron density over the ring. So some of the groups are NO2, CHO, CN, etc. So these withdrawing groups, they pull the electron towards them and decreases the electron density over the hydroxyl group. So this makes the phenoxide ion more stable when phenol loses the proton. So the electron withdrawing group, they helps to lose the proton. These groups increases the acidity of phenol by decreasing the electron density over the hydroxyl group. So let's know the effect of electron donating group on the acidity of phenol. So these are some of the electron donating groups like NH2, OH, etc. They give the electron to the ring and increases the electron density over the oxygen atom. And this destabilizes the phenoxide ion after releasing the proton from the phenol, and that makes the phenol difficult to lose the proton. So electron donating groups decreases the acidity of phenols by increasing the electron density over the oxygen atom.